Sir, is it visible?
Yeah, it's visible.
Yes, sir. This problem.
Okay. No, I understand, but what is your doubt?
Sir, there was a little bit confusion about handling the 7 equations.
Okay.
So there was some problem in the solutions. I understand the part how to write the equations, but
Mm-hmm.
there were some problems in the solving part.
Okay.
So if you get time in the last of the class, then can you repeat this once more?
No, I'll try to try to address this right away. Uh,
Okay, sir.
I hope everyone can see his screen. If not, just let me know. Is the screen visible to everyone? Can anyone
Yes, sir.
confirm?
Yes, sir. Yes, sir.
Okay. Okay. Can you zoom this image a bit?
Yes, sir. Sure.
Okay. So, so what I recall, I said was to consider this point F right here and this E right here. Okay. For Okay, let me check. So, let's say if I take this member GFC. Okay, so you understand this bottom portion, which is of gray color. Okay, and if I take moment about F, then I know one relation among the two forces that are at C. So I'll get one equation for Cx and Cy if I get the moment with respect to F. Next, if I move on to the member ECA and again take moment with respect to E, this time I'll get a second equation involving the component Cx and Cy. Those two equations are independent and therefore would let me calculate Cx and Cy. Okay. Those who have solved this, you can actually confirm that, let's say for the member GFC, at first I take moment about F. Okay. So that would be involving the force. Okay. Of course, I do not know the force at G right there. Okay. So yeah. So okay. So there is still equation, but that involves the force at G. Okay. So Cx and Cy are still not solved. Okay. Now, so now what we have is Cx and Cy in terms of in terms of the force that is at G. Okay, and then we can consider the rest of the equations of equilibrium to evaluate the forces at F and forces at E with respect to G. Okay. For example, the force at E can be evaluated with respect to uh, G. Okay, so let's see this sequence. If this sequence works, I would take first the member GFC. Okay, so what I'm going to do now is I'm about to share my screen. Okay. So can you see this thing on my screen properly?
Yes, sir. Then, sir, should I stop my sharing?
Yeah. Yes, you can share. Stop sharing your screen.
Okay, sir.
Okay. So I hope everyone can see my screen now. Okay. So what I'm now going to do is, let's say, I would take this member GFC. So words here somewhere is F. There is G. Okay. I'll not be considering uh, people are still joining and leaving. Anyways, so I'll not be considering the the wear that is there. I'll be considering the cutting force that is being required. So that would be a compressive force on the wear, and in return, the wear cutter gets a compressive force uh, also. So yeah, it could be confusing. So I'm just calling it a force P right there. Okay. Now I do not know the magnitude of this force P, but I know its direction. Okay, it is supposed to be normal to the surface. Okay. Um, and by knowing this distance, which is let's say from here, from G to F, so this is G, from G to F, I know how much is the horizontal distance, and that is 36. Vertically, from G to F is I believe 10 millimeter. Okay, so you can do all the Pythagoras equation and all. So to find out how much is the distance between F and G, so basically it would give you uh, mm, distance between F and G. Okay, so that distance would be square root of 36 squared plus 10 squared. Okay, so somewhere around, I guess, 37.4. Okay, I'm just guessing. So you can get the moment due to P in terms of P. Okay, of course there would be reaction forces at F, and you probably don't know how much is Fx and Fy, which is fine. And you probably also do not know how much are Cy and Cx. Uh, Now Cy would be acting at a height of 19 above F, and sorry, Cx, and Cy be acting at a distance of 46 millimeters horizontal. Okay, so you can get the you can actually get the moment due to F, moment due to all the forces about F. Okay, and that will actually give you a relation involving this 37.4 times P, which is counterclockwise, then this 46 Cy, and this minus 19 Cx equals 0, and that probably would give you, I mean, that is the equation that you are going to get. You see, there are three unknowns in this equation, okay, but only a single equation. Okay, but that still is one equation, right? So let that be one equation. Next, we can move on to this member, second member, ECA, which would be this. Okay. And you know at how much distance is this 20 Newton force is acting away from E, right? It is 21 plus 88. So this point is E, and this distance is about 109. Okay. Now on which are also acting your Cy and Cx. Okay. Please be careful with the direction. They're supposed to be opposite. And that opposite direction is the positive sign. Okay. I mean, if you took these to be positive sign, the opposite direction on the other component should be the positive sign. So for this one, you do moment about E. Okay. And this time, it would tell me that because C and D are about 21 millimeters from E, and E and A both are on the same height, so this height is again 19. So 19 Cx minus 21 Cy, and then minus 20 times 109 equals 0. Okay. Now that becomes the second equation involving those three unknowns. Okay. So also using these two equations, you cannot solve for all the three quantities, P, Cy, and Cx. In the end, our goal is to get P. Okay. But what you can try doing is sequentially write everything in terms of P. Okay.
Sir,
Yes.
so I almost did the same thing. Means there was a little difference in my approach. So I saw that throughout that problem, means whenever it is pressed or released, the point E is always stationary. So I can argue that Ex is always 0. And for that,
How no, sorry. Why is Ex always 0?
the
It is
point,
not necessary that EX will be 0.
Yeah,
the
it's not
point,
necessary.
sir, it is the hinge point, sir. It shouldn't move. Sir,
No, it
whenever
can move. It can
You
move.
see, let me finish. This whole body is in equilibrium and no point on this body is supposed to move. But does that mean any component of force should be 0? No. My suggestion is, a lot of such confusions would arise. Okay, while you try to solve different problems. For example, I can show you this problem.
okay, sir. Sir, then in that case, sir, we can write, means from the free body diagram only, that that the two fx means, sorry, ex, the addition of the two ex should be 0. So in that
Yeah,
argument,
that
we
is
can
true
say
for
that,
everywhere. That is true for everywhere. You see this this Cx right here, it is exactly cancelling this Cx right here. That is true for every point, but that doesn't make it a known quantity. That still remains remains an unknown. Okay. Acha, why I brought this second figure right here? For this second figure, there is one argument that makes ay to be 0. Sorry, ax to be 0, and that argument is symmetry. Okay. this entire problem, the second problem, is entirely symmetric about x-axis, okay, that passes through A, which basically means the two components that are taking part at the spin joint A, they could not be experiencing an x directional force in opposite direction because of the symmetry of the problem. That is, one body could not be feeling ax in the positive x, the other could not be feeling in the negative x, okay, because of the symmetry. This isn't the low, the geometry is symmetric, the loading is symmetric. That's what symmetry means. So in this situation, you can go with the argument that the x component of the force would be 0. Okay. And that is true. That is correct. Okay. But what I would suggest that don't assume anything. Okay. And go ahead and, assign arbitrary ax and ay. Okay. And let there be a solution. And at the end of the solution, you will see that ax automatically turns out to be 0. So whatever is 0, and by the way, this problem is not symmetric by any means. Okay. And I can guarantee you that ex is not trivially 0. Neither is fx. So in this, that argument itself is not working over here. But even if that were working, I would suggest that go by the standard method. Okay. If it is 0, show it to be 0. Okay. Achha. So let's get back to our point. So in these two equations, actually, you can eventually write Cx and Cy. I'm not going to the steps. You should be in a position to write this as m times p plus c, linear expressions. Okay. So m1 c1, m2 c2. You are definitely be able to get that expression. Basically, substitute for Cx and Cy with respect to P. Okay. Do you think that is doable? I'm pretty sure it is doable. Okay. So, for example, here you can substitute for Cx, let's say, with Cy. Okay. And in after that, you can get an expression of Cx with respect to Cy, and then you can substitute that expression over here, and then you have a relation between Cy and P. And then you can substitute that into the previous expression of Cx with respect to Cy. In that, you can substitute the expression for Cy. And eventually, you can get the expressions of Cy and Cx in terms of P. Okay. I know you are smart enough to, figure that out. Is it okay? That we can assume that we can, have the expressions in terms of P?
Yes, sir.
Okay. Achha. So, that means now in this this configuration, okay, so let's say this is our body number 1, this is our body number 2. In body number 2, body number 1, we have used how many equations of equilibrium? 1, right? We have taken equation of equilibrium, moment equation of equilibrium with respect to F. Okay, so we have already used up one equation of equilibrium. Okay, fine, but we are not interested in this body anymore, because all we had to do is to have a relation between Cx and Cy with respect to P. So that 12 equations of equilibrium that we are talking about, of which 2 are already rendered useless. We don't need the values of forces at F. So of course, if it is not a part of the question, unless of course it is a part of the question, then we need the value of F, but that we can do later. But at the time being, we don't need the other 2 equations. And actually, I can tell you that for the second body also, GED, I'm not going to am I going to use? No, I'm not going to use those set of, I don't need the free body diagram of GFD as well. I can tell you that. So I'm not also going to use those set of equations. So only 3 equations for the 2 each green body, and this 1 equation. So total 7 equations. So you see, from this we can these 2 equations. So for the second body, I've also used up 1 equation of equilibrium, but I have 2 other. and that I'll use simply to have you know Ey plus oh sorry, okay, I have not drawn the forces at E, such a mistake. So this is Ey and this one is Ex. So Ex minus Cx, Ey minus Cy minus 20. Okay. Now from these two equations, now if I substitute these two expressions into these two equations, I'll have Ex and Ey in terms of P. Individually, I'll have Ex and Ey in terms of P. Okay. So basically, I have two unknowns Ex and Ey. Okay, but both in terms of P. So P is my only unknown right now when it comes to E. Now let us draw the free body diagram of the component EDB. So here is your E, here is your D, and then there is your B. So you have again 20 Newton force here, two unknowns dx and dy over here. You have all the dimensions, but let's say from this you get Ex to be, let's say, m3p plus c3, and Ey to be, actually Ex is same as Cx. Okay, so it is m1 and c1, and over here it is m3p plus c3. So now you have at E this Ey and this Ex, whose expressions are given in terms of P. Okay, so at E the only unknown is P, at D there are two unknowns, and then there is B. Now you can take moment of the whole system with respect to D, and then right away you have the value of P. So you only need 5 equations, 1 and 2, 3 and 4, and then take the moment with respect to D, which is I don't know, 21 times Ey. Then this one is also acting counterclockwise. So what is the height? I'm just assuming that the green portions are symmetric. I mean identical. So the distance between E and C is same as E and D. So it is plus 19 Ex, all acting counterclockwise. Then plus 20 times, how much is the distance? 88. It should go to 0. Okay. So using this fifth equation, you can actually evaluate P. Okay. So you only need 5 equations of equilibrium to evaluate P. And once you have evaluated P, you can go to any component and evaluate rest of the forces. Okay. So does this make sense?
Yes, sir.
করা যাবে?
হ্যাঁ স্যার, আমি একবার ট্রাই করে দেখবো।
এখনো ট্রাই করে দেখবে? এই সবকটা ইকুয়েশন লিখে দিলাম, এখনো ট্রাই করে দেখবে?
না স্যার, মানে
এখনো
ক্যালকুলেশনটা
সলভ
করিনি,
করোনি কি?
ক্যালকুলেশনটা এখনো কমপ্লিট করিনি।
করে ফেলো।
হ্যাঁ
5
স্যার,
মিনিট সময় দিচ্ছি, করে ফেলো।
হ্যাঁ স্যার, হ্যাঁ স্যার, হ্যাঁ স্যার।
বাকিরা সবাই পেরেছো এই প্রবলেমটা? যারা পেরেছো খুব ভালো কথা, আর যারা পারোনি এই অবধি যেগুলো করা হলো, on the basis of that try to solve for p.
আমার তো ওরকম ভাবে মানে এসছিল কিন্তু এরকম ভুল ভাবে।
হ্যাঁ হ্যাঁ বলো।
স্যার আমার তো ওরকম ভাবে মানে আমি তো ওই আর্গুমেন্টে করে আমার এসছিল আমার।
না, ওই আর্গুমেন্টটা করে একদমই ঠিক আসেনি, তার কারণ তুমি একটা জিরো ইএক্স ধরে নিয়েছো, এখানে কিন্তু আমরা জিরো পাবো না। দেখো আমার আর্গুমেন্টের মধ্যে কোথাও তো ভুল নেই, আমি কিছু ধরে নিইনি, ঠিক আছে? এবার আমি যদি একটা নন জিরো ইএক্স পাই, ঠিক আছে, নন জিরো ইএক্স পেয়েই যাব যদি ধরো ফর এনি আর্বিট্রারি ভ্যালু অফ পি, মানে যখন আমি পিটা ক্যালকুলেট করবো আমি তো শিওরলি বলতে পারছি না, বিকজ ইএক্স ইজ গোয়িং টু বি সিএক্স, ওকে? So that would mean that I'm not sure whether it is going to be zero or not. But যদি non-zero হয়, then your answer is incorrect. Okay. So my suggestion is you should also try.
হ্যাঁ স্যার করছি স্যার।
Sir, I am getting 93.84 Newton.
About 94 Newton then.
Yes, sir.
Anyone else?
Sir,
Yes.
sir, I am getting 127.68.
Okay. Has anyone else tried?
Sir, I think it was a coincidence because I was wrong. But in this case, also CX was coming 0. I guess it was a
Okay.
coincidence.
Okay. Okay. So one who got 94, are you getting Cx equals 0 as well?
Sir, let me check.
So for that equation 3, I had multiplied 19 with the first equation, means the EX equation, and 21 with the second equation. Then I subtracted the first equation from the second equation.
Mm-hmm.
Uh, then was the term coming 19cx minus 21cy, which I replaced from this first number one number equation.
Mm-hmm.
Sorry, not now one number. Sorry, two number second equation. That 20 into 109. I replaced that value. Then I got
Okay.
21 ex minus 19. 21 ey minus 19 ex equals
Mm-hmm.
minus 1760, and
Okay. Fine.
from
Fine.
that.
You don't have to tell me the calculations. You don't have to tell me the calculations. So,
Sir, I am not getting Cx to be 0. It is coming minus 58.78.
okay. So anyone else tried solving the problem? Okay. So in that case, I don't know. So you can recheck your solution, both of you. Okay. I don't know which one is correct. And yes, as you mentioned, Cx could also be 0.
So do you have the answer? Means you can
No,
check
I
it
don't have
from
the
there.
answer. That is uh, a problem, but okay. Actually, I want to discuss another thing. Mm, so this is regarding the assignments. Okay, I hope you can see this PDF file right here. Okay. I've actually posted your grades and one image showing your performance uh, already in the classroom. Okay, so you can check that after the class, preferably. But I wanted to say a few things. The sort of mistakes that I have seen. I mean, that is you can say my explanation for the deductions. Okay, um, and what I'm not very happy about. I'm okay with you not attending my classes and you not even bothering to watch the YouTube videos, as long as you are able to solve problems correctly. Okay, and as was discussed before, assigning the assignment, that the purpose of that would be to check how good are you, how much understanding that you developed in drawing the free body diagrams. And mostly the gradings have been based on how the free body diagrams have been drawn. uh, so these are the type of mistakes that I have seen. So so let's say this figure 54 right here is very much the first problem in equilibrium. Okay, and two types of mistakes I have seen. Some of you put only oy component of reaction force. Okay, some of you put both reaction forces, but you see at O it's a fixed joint. Okay, it has to be. And without having a fixed joint, you cannot be applying so many loads and expect the body to be in equilibrium, which basically means if you write down all the three equations of equilibrium, assuming only two reaction forces, you will have an inconsistent system. Okay, uh, system of equations I'm talking about. So maybe in your calculation you have included the moment that is there as a reaction. So the complete diagram should be with two force reactions and one moment reaction. Maybe you have done that in your calculation, but you have not. Many of you have not shown it in your free body diagram, and that means it's an incorrect solution to the problem. Okay. So there is one type of mistake. The second type of mistake is that some other people did, and some people are there who did both. Okay, which was uh, to show the support itself. And on the very first day when we were discussing free body diagram, this was mentioned clearly that what is meant by free body diagram. I'll be removing one support and then be substituting with that. And as a substitute, I'll put the corresponding reactions. Okay, be it forces or moments. So the free body diagram has the rigid body of our attention, and then we have the reaction forces and moments coming from the support, but not the support itself. Now, having the support as well would make it an incorrect free body diagram. Second problem, same thing. Some of you have shown the nail as well. Okay, and you have made the nail a part of the free body diagram. Okay. Uh, Third problem also. In the third problem, some of you showed that circular peg, which is colored blue and which is behind the slotted plate right there, and we are supposed to draw the free body diagram on the slotted plate. Okay, and those who showed that circular peg right there, which is not the part of the rigid body, okay, that is an incorrect free body diagram, because that peg uh, being there, I mean, that is a support itself. The support must be removed from the free body diagram. One more thing, the force at B in this third diagram, figure number 56, it is supposed to be perpendicular to the axis of the slot. Okay, which means this line right here, which makes an angle of 30 degree with the vertical. And I've seen that I mean, even if you are correctly drawing it to be very close to a normal to that line, show a perpendicular sign. I mean, the way we show one line is a perpendicular to another, uh, to clarify that it is perpendicular to such direction. Now what I've seen is people drawing some arbitrary direction of FB, okay, as if FB is a pin joint. Okay, so that is incorrect. Again, the type of problem that we observed with figure 54, we have seen that with 57 also, is that at A, some of you are confused what sort of reactions should there be. Okay, because it's a welded joint, so isn't it supposed to be like all possible reactions, that is two forces and a moment. Okay, but you have not done that. Okay, what else? You have directly written the force coming at where the person is standing, but that requires the free body diagram of the person. Okay, so the person is pulling the cable, which has a tension of let's say some 100 or 300 Newton, whatever. So if you draw the free body diagram of the person, okay, and then calculate how much normal force is he receiving from the beam in order to be in equilibrium, and then put that normal force in the reverse direction on that location, that is justified. Okay, if not that done in that way, you cannot simply write whatever force that must apply to that location. Okay. Okay. Now, problem with figure number, I mostly skipped figure 60, because we have thoroughly discussed each and every diagram over here.
Sir,
Yes.
sir, one question, sir. Sir, we have to draw two diagrams, means one for the force and one for momentum, one for moment.
No, a single
Means
free body
we
diagram.
can
It should
show
be
that we can show both of them in the single diagram only.
I don't understand. Which problem are you talking about?
Means
Which
for
figure?
example, the first figure, if we are taking the moment about O, for example, then the 3 kilonewton force is creating a moment, 1.4 is creating
Okay,
a
let me
moment,
stop
and
you right there. Let me stop you right there. I'm not talking about the equivalent force system part of it. I'm talking about even the basic part of it, the free body diagram. Okay, where you show reaction forces and reaction moments coming from a given support by removing the support. So at O, it is fixed. So everything else in the diagram remains same. The free body diagram would be, I would remove this fixed support right here, and substitute that with the reactions that this fixed support is supposed to provide, which is prevent any sort of motion, which is two reaction force and one reaction moment, which
yes, sir.
directly apply at O. And then comes getting the equivalent force system. And now the way you are talking to me, it appears that you didn't even understand what we are doing in the equilibrium setup.
No, sir, I'm not talking about the point O.
Then
I'm not talking about point O. Means that force at point A is creating of external is, it is an external moment, means it is a creating a moment about point O,
Yes, it is.
and so is that force at C, and also a couple moment at B, because since a
Yes,
couple moment
yes.
it can be shown anywhere. So means we have to show these moments, means we have to like just like we show that couple moment through a circular arrow, we have to show that there is a moment due to that point A and point C in the FVD.
In the FVD, every external force should or moment should be there. In addition to, there should be the reaction force and moments coming from the support, while the support itself should not be there.
So that I did. So that I did.
Okay, so I hope I made myself clear there. Acha. One problem that I saw with figure 61 through 63, I mean, you are not supposed to draw the cables that go from B to D. You are only supposed to show the direction, and the way you do that is maybe through these broken lines. Okay, the way the axis and all the other directions have been shown. So you can use the broken lines to show that it's a direction. But in a free body diagram, you're not supposed to draw the cables themselves. Okay, some people have done that mistake. Others simply put all the forces and if there are moments, then moments correctly, but then without any dimension. Okay, both are incorrect. That means I should be showing all the coordinate triads, all the dimensions, and where is this point, where is this tensile load T1 going from point B to point D. Okay, I should be showing that direction as well. Uh, but how, let's say halfway between B and D, I'll be showing an arrow going from B to that direction. Okay. So I'll not be showing the entire line solid that would represent the cable. I would be showing broken lines from B to D, and from B to, let's say, halfway between B and D, I will be showing an arrow. Okay, so that would represent my tensile force. Okay, so these are the types of mistakes that I've seen from the problems involving cables. Okay, and some people even didn't understand the concept of free body diagram. They simply did a very rough and very mm, bad drawings of the problems themselves. Okay, and for them that was the free body diagram. At most the supports were removed, but no reaction force or moment were shown. I mean, those are totally incorrect free body diagrams. Okay, so my point is the grading has been done accordingly, and it ranges probably between 2 to 9.5 or something out of 10. So yes, so you can check what type of. So once you check your grades, you will know, and I hope there should not be any confusion why there has been deductions. But most of you are not attending my class, so yeah, so probably there would be some confusions. So let those confusions be. We'll proceed for our discussion with friction.
Sir,
Yes.
sir, I submitted the assignment, but it is not mentioned in the roll number list.
Okay. When did you submit? Did
Monday
you
evening.
Monday evening?
Yes, sir.
Okay, then I should have got it. What you can do is you can send it me over email.
Okay, sir. Thank you.
Okay.
Sir, even my one is not marked. My roll number is 1090 and 1190 is there.
Okay, so you can also send me your assignment sheet.
Okay, sir. Thank you.
Okay, so now friction, as we were discussing that is the the very last chapter that you do in equilibrium. But friction by no means is limited to equilibrium problems. Okay, and if I were to classify friction into various categories, uh, that would include fluid friction, solid friction, the one we are about to look into, and then there is material friction. Okay, and in any form, the purpose, I mean you know the function that friction serves, it opposes relative motion between relative motion at, I should be calling it at interface. Okay, so whenever two surfaces are about to have relative motion or actually having relative motion. Okay, I mean it covers the domains of both static and dynamic problems. So whether they are um, not having relative motion, but there is a tendency of relative motion, just like there was moment which would be trying to create a tendency of rotation similar to that. So tendency of relative motion is there, or there is an actual relative motion that would be opposed by friction. And friction basically is a force that acts opposite to that. And fluid friction, you are very much familiar with this term, which is called viscosity. So viscosity can be represented somewhat like this. Now I'll explain what these terms are. For example, uh, imagine there is a plate moving with, I mean, this example is not mandatory, but it kind of helps the point. Let's say it is moving with a velocity u 0, and then there is another plate that is stationary, and let's say there is a fluid trapped in between, and this fluid has something called fluids have something called um, no slip boundary condition. That means at the fluid solid interface, the velocity of the fluid and the velocity of the solid is supposed to be the same. Okay, and I'm considering a very trivial case of laminar flow. Okay, that need not be the case. But in any case, let's say if the upper one is stationary, uh, then you have this velocity distribution. This is how the velocity is changing. Okay, going on in between. So the point is the velocity is not uniform. Okay. And then if you can imagine that the fluid can be divided into, at an arbitrary height, the fluid can be divided into two portions. So at an arbitrary height of y, let's say, not h, so you can divide the fluid into two portions. Okay, one which is moving relative to other. So the friction force per unit area, as you can see, represented with tau, which represents shear stress. Okay, per unit area of friction force is represented like this, where mu is the viscosity. Okay, and what you have to do is take the slope of the velocity distribution. So this is how u is changing with y, and all you have to do is get the slope of this, okay, and that slope times the viscosity gives you the shear force. So that is fluid friction. And one thing to notice is that that is rate dependent. That means it is dependent on the velocity of the fluid. Number one. Now this comes under the very limited category of Newtonian fluid. And there are a lot of non-Newtonian fluid, you must be familiar, where such linear relationship do not exist. Okay, such linear relationship that goes past the origin so that is not the case all the time. Sometimes they have x or y intercept, okay, and most of the times they are non-linear. And there are different categories of viscosity, okay, and this happens to be the type of Newtonian fluids. And as we discussed earlier, so this friction force, if you can mentally divide the fluid into two portions, one moving relative to the other. Let's say the top portion is moving towards the right relative to the bottom portion, okay. So on the top portion, the friction force would be acting in the negative y direction, and in the bottom portion it will be acting in the positive y direction. In other way, that the bottom portion of the fluid is trying to slow down the top portion, and the top portion is trying to pull the bottom half of the fluid. Now that goes for the fluid friction, and solid friction is what we are about to discuss in today's class. But before going there, let's talk about material friction. In simple word, material friction is nothing but plasticity. Okay. So mostly here we are talking about metal plasticity, let's say. So this is how metals deform, and I'm trying to plot here the stress versus strain. Stress, as you know, is the force per unit area, and strain, you can say, deflection per unit length. And that in the first part obeys Hooke's law, but up to, let's say, a given point, which is the limit of elasticity, a so-called elastic limit, can be approximated as something called an yield stress. And beyond yield stress, the stress changes with strain with a much flatter slope. Okay, much flatter slope. It's like this. And many times we approximate that to be elastic, perfectly plastic situation. So that basically is a flat line beyond the elastic part. And so this basically, so friction, as you might know, that is associated with loss in mechanical energy. So mechanical energy is dissipated through friction. And how do I know plasticity is friction? Because when you try to unload in plasticity, let's say you load it like this, and if you are to unload in elasticity, you follow the same curve. But if you want to unload in plasticity, you follow this, this this steep line right here, which is parallel to the elastic part of the curve. And because you see this area under the curve represents this integration f du 1 by al, which basically means v. So this area under the curve is once you unload it, it represents the amount of work done that has gone into vain, okay, or the amount of energy lost in the process, okay. And this basically is the nature of friction, okay. And solid friction, of course, you are intuitively familiar with friction. So for example, if you have this brick lying on the on this ground right here, and you applied certain force to it, okay, and brought it to let's say over here at a distance away from it, okay, and then you removed your finger, okay. Now the amount of work that was done on this body to be moved from this place to this place, okay, that energy is also lost in the process, okay, much like what happens in plasticity. Of course, in plasticity there are not literally like contacting surfaces and all. There are surfaces, um, there are planes, there are of course sources of roughness, okay, but uh, not in the literal sense of roughness, okay. So that is there. Now plasticity can be of various types. Plasticity can be rate independent. That means it doesn't depend on at which rate are you applying this displacement or strain right here, or it could be rate dependent, and when it is rate dependent, it is often called viscoplasticity. You see, viscosity plus plasticity. Okay, and when you talk about viscoplasticity, any fluid is also comes under the domain of viscoplasticity. Okay, actually they come under the domain of something bigger called rheology. Okay, which is study of everything related to material and fluid friction. Now let's get back to solid friction, or so-called Coulomb friction. In this case, the friction force is self-adjusting. Now, what is friction force? Let's say if I apply a force, it is stationary, and if I apply a force P right here, so if I want to draw the free body diagram of the body, of course, either the reason it is touching the ground is either because of its weight or anything else. It has some normal force developing on the surface. Okay, I mean this P right here could also have a component in a different direction, but it's the net normal force that is coming from the surface that matters. Okay, so proportional to that force, actually not proportional to that force, uh, so there is in addition another force, self-adjusting force, friction is acting. Okay, and when the body is in equilibrium, P equals F in equilibrium, and F simply is self-adjusting. It is just the amount enough, okay, to keep the body in equilibrium. Okay, for example, uh, for example, let's say if you are trying to move a table, okay, and you are applying some horizontal force to it, and it has still not moved. It is about to move maybe, but it has still not moved. But all this while, okay, friction was simply leveling it up to balance whatever external force that you are applying. Okay, so it simply can change. It is anything. Okay, uh, and as we discussed earlier, that frictional support is as good as a pin joint, because there are two unknown forces, both N and F are unknown. But one thing is known about F, that the limiting value of F is mu s times m. And when you indeed apply P, which is mu s times n, okay, the block actually starts moving. Okay, and actually at that point is goes from the domain of static friction to kinetic friction. Okay, um, and in that situation, the coefficient of kinetic friction. So in that situation, F becomes equal to mu k times n, and it cannot change from this value. Okay, and coefficient of kinetic friction is typically smaller than mu s. Okay, slightly. So this is what happens when it comes to, if I plot F versus P. So initially they are the same. Then you go past the critical value, which is mu s times n, and then it slightly decreases and becomes nearly fixed. So this is mu k times n. Now, of course, that means if I do sigma fx, which would be p minus f, okay, and if p cannot go beyond this value, and f cannot go beyond this value, and p keeps on increasing following the original line, p keeps on increasing. So this is f equal p line. Okay, so this basically, so there is a difference between f and p right now. So this is the actual f. So this difference, p minus f, what does that do? So that unbalanced force actually accelerates the body in motion. Okay, and if I keep on increasing p, this is what we would expect. Okay, after we reach certain huge value. But if you do not consider that extreme situation, for can you see certain similarity between these two diagrams? One which is material friction, the other one which is actually the solid friction. So of course, here the x-axis is displacement. Here the x-axis is a force, but you see the nature of the curve is very similar. And actually, you can also think of this p in terms of deflection. If you attach a spring to it and then apply p from over there. Okay, so as p changes, the spring will elongate. Okay, and then you have the plot of F versus that deflection. That would be very similar to this one. Okay, and actually, if you can also understand that once I remove this p, once this F becomes 0, the block doesn't go back to its original position. So it just remains there. So whatever energy that you had spent in moving the block from one part to another, that energy is lost, much like this this area under the curve. Okay, so all I'm trying to do here is to give you a comparison between the material friction and the solid friction. Okay, and just a while ago we were talking about roughness. So if we really zoom into the roughness part of it, so the roughness can be thought of see the non-uniformity of the surface, okay, which come in contact with the another non-uniform surface, which is, let's say, the bottom of the block, okay, at various angles. Okay, so let's say this is the angle at which the contact happens. Okay, so you can imagine at so those roughnesses, you can imagine that once you close into a given roughness, you can imagine that that itself is frictionless. But since it is not vertical, okay, so it provides force reaction to the body at this angle, okay, let's call this angle phi. Okay, and the horizontal component of this force, okay, let's call this force as R. Okay, so the horizontal component of this force is essentially the so-called friction force. Okay, now you can do that for each contact pair of the two rough surfaces. So you can give them name Ri and Fi. So the net friction force is essentially your summation over Ri sine phi I. Okay, and in the end you can have the total resultant force and an equivalent angle. So this angle is called a friction angle. So in the end you can say that that for this block also, instead of showing separate normal and friction force, you can show that by a single resultant. Okay, and then by an angle. Okay, and when the block actually starts is in the limit of static friction. Okay, uh, so this phi is this tan of phi is actually mu s. This relation you should also be familiar with. So when the block is about to start moving, okay, coming from the domains of equilibrium. So when the two surfaces are about to have relative motion, that's when this tan phi is mu s. Okay, and which basically means this f by n becomes mu s in that situation. Okay, now this part of the story you are already familiar with. Just keep in mind one thing, that friction is not always mu s times n in equilibrium. It can be anything, but the absolute value is smaller than mu s times n. Okay, so just keep that in mind while we do the set of problems that you are about to do. Okay, so I guess there is no question regarding this part, right? Okay. So this block weighs 100 kg. Okay. Sorry, not 100 kg. Sorry. No, sorry. So you see this block right here. This one weighs 100 lb. Okay, and actually the question is to find out the limits on W. Okay, so what should be the limits on W so that the system remains in equilibrium? And how do you propose to solve this problem? and both the coefficient of static and kinetic friction are given over here. Now, of course, this involves, because it's an equilibrium problem, okay, this involves drawing free body diagram and all, okay, but few of the things that is kind of you can assume, if not mentioned, and hopefully it will always be mentioned. One thing is that the wheels can be assumed frictionless, the pulleys can be assumed frictionless. So these are all frictionless. The wheel, the pulley, and this pulley right here, these are all frictionless. Okay, and then there is this 100 lb weight on this other side. Okay, now what should be the W over here in order for the system to be in equilibrium, or what range can it be? How do you think should we use the static or the kinetic coefficient of friction in this case?
Only the coefficient of static friction would.
Sorry?
Sir, we would only use the coefficient of static friction.
Okay. So we'll only use the coefficient of static friction, which is okay. And anything else you want to add? How do you propose to solve this one? What is the strategy?
By drawing two FBDs.
Sir, I have found out.
Yes.
Sir, why there should be some W minimum? It can
Why?
be any mass less than W max.
Okay.
Now, if
Yes.
W is too small, then the pulley will roll.
It will move in the opposite direction. It will move upwards.
Yes.
Oh,
So
yes.
So the answer here is
friction in upward and one time is downward.
yes. So the situation is that by being in equilibrium, it means that it is not moving either in the left or in the right. That means this 100 lb weight is not pulling this other weight upwards, or is not being pulled by the other weight. Okay. So when the system tries to move, the whole system tries to move, about to move in the left, that's when we will have W mean. And when the whole system is about to move in the right, that's when we have W max. Okay. Now, one thing that I have not shown that you already know, but let's say you have a pulley, okay, and then there is a cable, and the cable is has gone a full turn or maybe a couple of them, and let's say they on the other side it has this direction, okay, and the tension in the pulley, tension in that cable is, let's say, T1 over here and T2 on this side, let's say. Okay, then what I can do is, with respect to the center, I can draw, I can, of course, it is receiving other forces at the center, okay, other forces that are kind of, this force which is keeping the object in equilibrium, which is minus T1 plus T2 vectors. Now, that the fact that the magnitude of T1 and T2 are same, and that is only true for a frictionless pulley, is when you show that the moment about O has to be 0, and that doesn't require this T1 plus T2 right here, and that requires only R times T1 minus R times T2 to be 0, which basically gives us T1 equals T2 for a frictionless pulley. What happens when there is friction? Because then we'll also have to account for the friction force. Okay. So the friction force also takes into, goes into the moment calculation. And then if let's say T1 is greater than T2, the rest is balanced by this moment. Okay, sorry, this friction force. The rest of the moment is balanced by this friction. So by assuming a frictionless pulley, we can safely assume that on either side it is the same tension. Okay. So we have to draw free body diagram of both bodies. So let's say with 100 lb body, let's call it A. For this one, there is a downward force 100 lb. Okay, and this side makes an angle of 20 degree with the horizontal. So to normal to that, I know this set of problems are your territory because you have done a lot of problems with friction in your class 2 studies. But please keep in mind that so far, even in this example, all the problems that we are doing are considering the bodies to be particles. We're still not concerned about the dimension of the object. Okay, so there is a normal force, and let's say we are considering now the direction of the friction force would depend on cases. Let's say case 1. So that's when we say that system moves left. That is, we are trying to find out W mean. If the system moves left, the friction force acts in right. Okay. So this is a free body diagram of the one block. The other block, which is slightly tilted, and please note how am I showing the direction? By taking broken lines just to represent the directions. Okay, I'm not drawing solid lines. That would mean I'm drawing the surface. I'm not doing that. So it is receiving some N2 normal force. Okay. Achha, this receiving 2T horizontal, 2T force along the slope. Over here it is receiving T. And then it has its own weight W. Okay. Now this free body diagram, FBD2, is same in either case. But in case 2, the free body diagram of the first block will be different, that the friction force would act in the opposite direction when we are considering that the W is pulling the 100 lb weight on the right. Okay, so when we are trying to get the W max. Okay, so you can do the case 2 as an assignment, but can you at least get the value of W for case 1? You see,
Sir?
Yeah, let me just finish one more thing. Since we are here all considering, objects which are tiny, which means we are only considering particles here, we only be dealing with 2 equations of equilibrium, sigma fx and sigma fy, and that fx and fy are also of your choice. For example, you can take x prime and y prime and call this direction as x prime and this direction as y prime. Similarly, you can that is not required for the second body, but let's say for this one you can consider this to be x double prime and this one to be y double prime, and take everything in x double prime y double prime coordinate. Okay, there needs to be 2 orthogonal coordinates. That's just 2 orthogonal direction. That is the only requirement. Yes, you can carry on.
Sir, my W max was coming 31.678 pounds. And W mean was coming 3.
1.678 what?
Sir, LBF.
LBF, okay. And
the W mean was coming 3.051 LBF.
the answers are correct. I'm only concerned about whether you are getting the free body diagrams correctly, whether you are writing equations of equilibrium consistently. I know you can solve this problem. I know you can solve this problem the way you need to solve them in order to answer MCQs. Okay. So I'm okay with the first part that you can solve this problem, but I'm not okay with the second part that you know how to solve them like you are answering MCQs. Okay. So because you won't be answering MCQs. So yeah, so you need to work on the second part. That is something I'm more concerned with. Okay. Uh, okay. So I believe you can write your own set of equations of equilibrium considering your own set of coordinates. For this problem, actually, I remember the answers, so I can verify whether the answers are correct or not. Yes, the answers are correct. 3 and 31 are correct. Okay, so could you at least get W mean? Is there anyone else who got W mean?
Yes, sir. That is 3.05.
Yes, sir. I am also getting the 3.05.
Okay. Okay, so let's move on to next problem. Okay. So this wheel weighs 25 kg. Okay. And the question is determine M such that I mean the value of M required to create a relative motion between the ground and the wheel. Okay. So I hope you understand what's happening over here. So this member AB, and I hope you can identify this to be a two-force member, is pinned with ground at A and pinned with the wheel at B, which basically means if not for friction, the wheel can rotate. And of course, AB will also have to rotate when wheel rotates. Uh, but in presence, wheel can rotate freely in absence of friction. But since there is friction, it cannot freely rotate. There has to be a certain non-zero moment before the wheel starts rotating. And that non-zero moment is what we are required to solve. Okay. So this is how we would be drawing the free body diagram of the wheel. Okay. So here is the center. Let's call it O. And the radius is 0.15 meter. Now, because AB is a two-force member, the force P acts along AB, okay, and basically what is the direction? The direction is, if I were to give the direction, that would be so 3:4:5. Okay, that is a slope. So 250 and 150, right? So 3:4:5 is the gives you the slope of the force at B. And then there is a moment externally applied. And since it is in contact with the ground, it is receiving certain normal and frictional force. So let's say this is the normal force in, and this is the friction force F. And just because there is a normal force and the disk weighs certain value, so how much that would be? Maybe this much Newton, because it weighs a certain Newton, that doesn't mean that is going to be the normal force. Okay, so the force at B will also going to be contributing to N. Okay, and don't just think in that way and try to get the value of N. Write proper equations of equilibrium like sigma Fy equals 0. Okay, let that tell you how much would be your N. Then sigma Fx is 0. So the disk is still in equilibrium, but it is about to have relative motion. It's on the verge of having relative motion. Okay, but it's still in equilibrium, which basically means that that force B over there, its component -3/5. Okay, and then the only horizontal force is F. So minus F equals 0. I probably drew the friction force incorrectly. No, friction force is correct. I just drew the friction force is correct, but I just drew the force coming from the two force member incorrectly. Okay, so what I can also change that, like I can show it to be like this. Okay, then I don't have to use this negative sign right here. Now that is not mandatory. I can go ahead with the negative sign, and ultimately I'll get a negative value. But when it comes to friction, not showing the correct direction can be a problem. So for friction, you need to figure out in which direction we are about to have relative motion, and in that case, in which direction should the friction force act, and the direction of the friction force should be correct. Okay, Acha, you might have noticed that that I'm not writing mu s times n in place of friction, which I could be, because it's definitely going to be relative, be the limiting friction, because the disk is about to have relative motion. Okay, because that is my so you see in this problem there are 4 unknowns: B, N, and F. There are 4 unknowns, right? So I'm not simply I have 3 equations of equilibrium. Okay, so I can get, let's say, moment about Z, and that I can get about any force, any point. So I might choose to take this point of contact C over here. Okay, that would save me a lot of effort actually. So let's say moment about C. I can take moment about C. Um, so I can have three equations of equilibrium, but four unknowns to solve for. Of course, the fourth equation, also known as the constraint equation, is this: F equals mu s times n. Okay. And it always has to be F equals plus mu s times n. It's not plus or minus. Okay. And that means I'll have to figure out the direction of the friction force. Just like in the previous problem also, I had to draw two separate free body diagrams for two different cases. With friction force, you need to know the direction of the force. Okay. I mean, when it is about to have, it is on the verge of having relative motion. Okay. Earlier, when we knew that there was not going to be any relative motion, okay, like a general equilibrium problem, where a frictional support was as good as a pin joint, there I didn't have to know the direction of the friction force. But this time, when I'm about to have a relative motion, okay, then I need to know the direction of the friction force. So yes, uh, so that is our fourth equation. Okay, will not be showing F equals mu s times n in the free body diagram, but we can write them in association with all the equations of equilibrium, and that way we can solve for all the unknowns. Okay. Here our goal is to find out that the minimum moment that is required to cause any relative motion. So for that, so from the first equation we'll get the normal force. The second equation will give us the force at B, and from third equation we can get the moment value.
Sir,
Yes.
so one doubt. Um, Sir, how can we calculate the normal force without calculating B? Because there is a y component of the
Y component of B, right? Y
yes,
component of
yes,
B.
yes, sir.
Okay, so probably we'll have to solve both of them together. Actually, these two equation number one, equation number two, and equation number three simultaneously. So basically, you have to substitute for F over here, and from the first equation you are not getting in, so you'll have to solve all of them together to get the value of the two unknowns, because now you have substituted for F the two unknowns n and b simultaneously. If you were to get
The value of mu s is given, or we have to
mu s
check
is
it?
given. I didn't give you, right? Mu s is 0.4. Achha, can you tell me, is there a way to get value of the normal force without getting the value of B? I think there is a way. Of course, you need to incorporate this equation. What you can do is you can resolve the forces in x prime and y prime coordinate system. And actually, by taking the uh, y prime components of all the forces, okay, would prevent any term of B in your equation. And that way you can directly figure out what is the normal force. Okay, and later you can take the moment with respect to B. Okay, and then from that you can figure out the moment without even evaluating the force at B. Okay, so I believe you can also solve this problem And today we'll stop here, and we have 3 to 4 more problems to solve. Okay, that we will do in the next class.